So good afternoon, everyone. It's truly an honor to be here and standing before you in this audience that have some of the people that actually inspire me in my journey into MPS. And I embarked into my independent career approximately 3 years ago when I became an assistant professor at the University of Cincinnati. And since then, I started making a strategic decision to adopting a 3D bioprinting approach toward generating of our MPS models. And today I will show you some of the results we generated in our lab. When compared to traditional self-lithography methods borrowed from electronic industry, 3D printing and bioprinting allow us for rapid prototyping and scaling up of organ-on-chip system with ease. And moreover, this approach facilitates the transition toward building of PDMS-free devices, what are known to absorb less molecule. I'm going to show you some evidence later today. And also, we can combine 3D printing technologies and bioprinting technologies to have, I don't know if you see the mouse. Well, to have more complex geometries. Again, making PDMS-free devices that are still perfusive, or even incorporate new readouts, such as electrochemical readouts. This is an example of a scaffold of our device that now incorporate electrochemical sensors. I'm fortunate to lead a dedicated team of graduate and undergrad students in my lab, and I would like to take a moment to quickly introduce them to you with the slides. In particular, thanks also one of the members of our team, Sujana Poon, who today is in the audience and who had the chance to present her work yesterday during the poster session. In Cincinnati, we have access to two leading institutions, the University of Cincinnati, where my lab is hosted in the biomedical engineering department. But we also have access to the Cincinnati Children's Hospital. In fact, we also have space that is hosted by the Center of Organoid Medicine, stem cells and organoid medicine, or CUSTOM. And this is a highly collaborative space that helps me fostering a truly interdisciplinary research environment and enable us to have access to multiple research facilities in the same area. So what we do is to use a simple one-step bioprinting approach to generate simple designs such as the blood vessel chips that consist in simple straight microfluidic channel lined with endothelial cells. And in this case, this method consists first in generating a border made of PDMS, as you can see in this picture here. I hope you can see that. This is a border entirely made of silicon material that is a printable PDMS. Formulated for 3D bioprinting extrusion. And secondly, we can use sacrificial materials such as pluronic, a method previously published over 10 years ago by a group of Jennifer Lewis at Davis, as in the picture on the right. And in that way, we can literally print channels made of pluronic that secondly are coated with PDMS. The PDMS will cure and the pluronic can be removed easily. So you end up with this hollow channel that you can seed with cells when you're ready for. This technique takes about an hour, and so in an hour or less we can test prototypes. So you can imagine the same day we can test a number of different interactions and optimize our device, a new concept easily. We are not limited to use only. Is it moving? Maybe. Okay. We are not limited to printing only straight channels, but we can print also more complex geometries, such as in this example where we printed one of our students printed more kind of wavy channels and even an open top design. Or we can also adapt multiple materials, as in the other example on the bottom, in which we have a solid scaffold made of PDMS that also has inlets incorporated. These inlets are then connected to each other toward microfluidic channels that can be generated using also hydrogels such as collagen or fibrin. So in this case, you're seeing a system that has three materials, as PDMS, pluronic inside in these pictures, and an hydrogel that holds a microfluidic channel inside. Now, one of the limitations of this technique is that if you want to generate something like this with 3 different materials, more complex kind of designs, that will take up to 1 hour just to print it, and then you need to cure and do all that process. So it's a great method for prototyping, but at least in our experience, it's not great if you want to scale the system, if you want to scale up the system. So when we want to scale up our devices and designs, then we turn into a more let's say, robust and established 3D printing method that adopts stereolithography technology. And so using SLA 3D printing, we can easily obtain a number of molds, as in this case, that can be processed and used for generating PDMS-based device, if I find the mouse, otherwise I use my hands. And so there are challenges, however, with this technique. And if you have any experience with 3D printing, we know that most of the resins, for instance, are toxic to cells. Plus, usually the surface of this material is rough. You have ridges. And so we optimize method to clean up our device and extract all the toxic compounds and even coat it with commercially available coating solutions, so we end up having a small surface that we can use then finally to molding our chips. This is an example of how we characterize our models. So cell viability can be easily accessed via standard live imaging or live dead assay, or even MTT-assay or Presto Blue. The cells, endothelial cells, in this case UVEX, but we also tested brain endothelial cells as well as iPSCs and derived endothelial cells. They all grow, forming a nice monolayer within a couple of days. And obviously stimulated with interleukin-1 or other inflammatory molecules on the response by upregulation of PKAM1 and other inflammatory biomarkers. And extensive inflammation can also clearly cause loss of tissue integrity, formation of these gaps. And if you flow blood through the system, and it's pretty obvious that healthy endothelium will not allow platelets to adhere nearly at all. So providing an antithrombotic surface, as you will expect from an healthy tissue. But if you inflame the endothelium with interleukin-1, as in this example, then fibrin and platelets will immediately stick to it. You have formation of larger platelets aggregating green and fibrin. And here we basically use this method to validate our systems. And now I would like to switch gear towards some more translation application of this device that we recently started to explore together with our collaborators, both children at AUC. In this case, I will show you some results that obtained from a collaboration with Elisa Vascular, which is a PI at Cincinnati Children. And our group is basically involved in research concerning a rare form of genetically inherited vascular anomaly that affects children in pediatric age. What they found out and recently published is that there is a mutation of a specific gene, we call GNAC, that it results in aberrant vascular morphology and aberrant blood clottings. So as you can see from this mouse model that they developed, what they found out is that when they induced the mutation using an induced promoter, a genetically modified mouse in which the mutation is under an inducible promoter, not only the blood vessels look abnormal, but also the clots. Also inside this blood vessel, you can find clots that are rich in red blood cells. And occasionally some red blood cells is also found outside of the vessels because the endothelium, it's not contiguous, it's a very leaky endothelium, it's weak. And so we worked together to try to recapitulate that with a more human-relevant system. And so the first thing is that we did is to use some of the endothelial cells, human endothelial cells this time, that have been genetically modified to integrate the same inducible mutation. And well, the first things that they've shown before working together with us, is that the mutation itself causes a reduction in the expression of B cadherin. And so that's probably the reason why this endothelium is so leaky. And so when we see these endothelial cells, that we induce the mutation in the same manner you will do in other systems. First of all, the endothelium starts to look a lot more patchy than our control. And secondly, if you flow human blood, healthy human blood through the system, just because the cells are now expressing these mutate genes, you have an increase in platelet and fibrin addition, which is aligned with the mouse model. The results obtained through the mouse model. So we're continuing exploring. We basically established a tool to further dive into the disease mechanism that it's hard to do with a mouse. Secondly, I'm going to show part of our work, it's dedicated also to provide a better understanding of the mechanism underlying vaccine-induced thrombosis and thrombopenia, which is a rare form of vaccine-induced toxicity. And so the mechanism is not completely understood yet. Sorry, I have issues with my mouse. So the current working hypothesis, however, is that most of people that are vaccinated with adenoviral vaccine usually tend to generate antibodies against the spike protein. That's the basis of the immunity against the COVID virus. But occasionally, as depicted in step 5, some people tend to respond with this VITT, or vaccine-induced thrombosis and thrombopenia. And there are clinical evidences indicating that this event is associated with the presence of autoimmune antibodies against platelet factor 4, a condition often referred as HIT, or heparin-induced thrombosis. But the relation between how these antibodies and the vaccine interact to form the clot is not completely clear yet. And so what we're trying to understand is if we can use our organ-on-chip-based approach to dissect this mechanism. And so the first things we did is to start working toward validating, or at least qualifying, our system to actually study this sort of blood clotting events that are now generated not because the endothelium is inflamed per se, but because something happened in the blood, right? And so what we did is to first work to reconstitute this the traditional HIT mechanism that rely on the presence of these autoimmune antibodies, or HIT antibodies, able to interact with platelet factor 4 only when heparin is also there. So what we did, and those experiments have been repeated in multiple donors, is to optimize a model. I'm not going in the technical details, but I'm happy to talk to you about later, to optimize a method to recreate this condition. And what we observe is that after a few steps of optimization, if you combine autoimmune antibodies obtained from patients with platelet factor 4 and heparin, we are able to reconstitute this sort of blood clotting events that mostly, as you can see from the imaging, consist in platelet addition to the endothelial cells. You won't see any fibrin here, as opposed to our positive control that consists in soluble collagen and epinephrine directly administered in the blood. And that's quite normal because heparin is in the system, and heparin is a strong anticoagulant. It will block the formation of fibrin because it inhibits the thrombin. But platelet addition is consistently found upregulated in all the conditions we tested and across 4 different donors at this time. So what we'll do next is essentially try to replace heparin with different components of the vaccines, because the question we're going after is, okay, we can recapitulate this HIT-based mechanism now. If instead of heparin we provide different components of the vaccine, such as the DNA or the capsid, are we able to see the same effect? Because if we're able to see that, we can say we have a way to recapitulate the ITT and maybe provide new indication for either producing new antibodies or new vaccines that can help, can be a little less risky. Plus, we could have a technology that in the future could be implemented in the vaccine development pipeline. One last thing I like to just touch base briefly for reason of time, but I have a few slides if you have questions, and I'm happy to pull them later. It's our efforts toward 3D-Bioprinting of macrophage model of glioblastoma. And in this project, which is an highly multidisciplinary project, where we work also with clinical scientists and physicians on campus, we were able to integrate different cell types, including first cell lines, obviously, and more recently, patient-derived samples in our devices that consist in combinational 3D and bioprinting strategies. Sujana Boone, as I mentioned before, has shown her poster yesterday. And I will, at this time, mostly focus on the strategy we adopt to build this model. What we're doing is, in fact, use SLA 3D printing to generate an entire microfluidic scaffold, as you can see in these pictures here. It's very easy to scale up this model. It's not that easy to prototype at the beginning because just to have a microfluidic channel inside, it took us a few iterations. But once we have it, we can now nearly mass produce it. We can have 50 of them in the same day, essentially. And this microfluidic scaffold is further interfaced with a microfluidic hydrogel that we generate with the pluronic method I briefly introduced you before. We print a line of pluronic, we cast an hydrogel, it can be fibrin, can be collagen hydrogel, that polymerize, and you end up with a microfluidic hydrogel that now is interfaced with a rigid scaffold that also hold these inlets as per design. They're here. And so the inlets can be easily connected to microfluidic systems, as in the picture, and connectors. One of the advantages of this model in respect to classic PDMS device, as I mentioned before, is that absorption of small molecule is limited. What we did here, to be consistent with the project we're working on, is to test the absorption of temozolomide with OTMZ, which is a small molecule and leading compound for treatment of GBM, which is normally largely absorbed by PDMS, at least in the first hour of treatment, but it's not absorbed, or nearly not absorbed in our device. These are results from mass spectrometry, 3 different experiments. I just averaged them. And so that's all the promising generative model can be used for testing of different small molecule or combined therapies for GBM. I will stop here and just acknowledge my findings in this last slides and my collaborators. As I said, we are very interdisciplinary groups that include also clinical physicians such as Shama Saginta, which is an expert in GBM, and translational scientists such as Elisa Pascolo, I just mentioned before, and others. And thank you all for your time, and I'm happy to take questions.
Thank you very much. Question, did you use cells in the bioink to print them, or you just printed chips, in which case this is 3D printing and it's not 3D bioprinting? Can you clarify?
Oh, good question. We do both, depends on the stage. So we still adopt, let's say, an organochimp approach. So sometimes what you do, you start with one cell types and then you add others. So we can, for instance, add an hydrogel. We can print a gelatin hyaluronic acid hydrogel that already have cells in it, so you can print it. But then you want to see the endothelial cells maybe at a later time point, so then you can see the endothelial cells in the device. So what we can do is to have an hydrogel here that has cells, and we can print that, and then we will add endothelial cells to the microfluidic channel at the second time point.
Yeah, I just want to be careful with the terminology. So when you're doing the chips without cells, that's 3D printing. We cannot call it 3D bioprinting. When you are using cells in your bioink, then we can call it 3D bioprinting.
Yeah, so what I'm saying is we do bioprinting in some projects. In this case, it's a fibrin hydrogel. In others, we have hydrogel that holds, for instance, spheroids, and we print them. We print the hydrogel with the spheroids. So this part is still 3D printed. But the hydrogel inside is a combination of gel mahama and spheroids. So that's bioprinting, right?
Right. But the chips themselves, they're 3D printed, not bioprinted. The ones you presented in the beginning.
I think that depends on the definitions, right?
Well, the definition of 3D bioprinting is using cells or cellular element,
but
right?
To me, the organochip is it all. It's a unit. It's not just the scaffold.
Thank you. I must concur with the question that you were asked. I mean, I think that you need to separate the two matters. But anyway, I mean, my question is not about that. You recognize that there's an issue when you use SLA printers because there's residual monomer that is not fully polymerized. And apparently you do some sort of washing, which also smooths. I imagine that you're using an organic solvent to do that. But that process is not perfect. And have you had the chance, or would you have the ability to look into what leaches, what monomers still leach after that process? Because, I mean, those may interfere with your biologic system.
Yeah, so with that technique, one of the main challenges at the beginning, I'm sure you know, if you cast PDMS over the print part, the PDMS are going to polymerize, because for some reason the things that are leached out from the print part block the PDMS polymerization. It was new to me, but when looking at the literature, I found out that people saw the same things. So if you wash it a few times overnight with different solvents, you remove most of these leaching components. I don't know exactly what leach out. Other people have done some of this.
Speak to the mic.
Sorry. So I was saying, yes, we address some of the issue with the leaching. I don't know exactly what leach out from the 3D print parts. But something very obvious is if you take just the 3D print part and you cast PDMS, it won't even polymerize because the molecule leach out will block even the polymerization, plus it's extremely toxic. So if you rinse a few times with some like isopropanol and other compounds, you can remove most of these molecules. But then what we do is also to coat it with a commercial available coating to further keep them away from leaching into the PDMS. And so far, this has been doing fine. I don't know exactly what leach out.
Yeah, I didn't realize that you were actually coating, because, I mean, I would be concerned about epoxidic monomers, which are highly reactive, slowly leaching out into your media, into your cells, and actually triggering a biologic response.
They do. In fact, the first month of Syngenta was watching cells dying into that.
So I'll just ask one more question, but related to that subject. So I was wondering, when you wash your chips, have you ever tried also putting them at higher temperatures? Because there are some studies that say that when you put them at, for example, 120 degrees for several hours, you can actually pretty much completely reduce any types of...
We do both.
Yeah, okay.
We do both. That is also part of our surface activation, because there are things, I'm not going to the details right now, but there are things is also the hydrogel won't stick to the 3D print part unless you you do a complete treatment of the parts. So that's also part of it.
Well, thank you again, and let's give him a round of applause for this great talk.